Hello everyone, this is Rekha Venkateshwarlu, Assistant Professor of Physics from Government Degree College Women, Nalgonda. Today, I am going to discuss about the topic electrostatics. This is BSc final year 5th semester electromagnetism syllabus. This is the first unit of that paper. The lesson plan of my talk is, yes, I think you're seeing the slide. The lesson plan of my talk is the first introduction, electric charge and properties. Then we will discuss the Coulombs inverse square law and mathematical expression. Then after electric field types and examples. After that, we will discuss the electric lines of force characteristics. The lastly conclusions.
Start.
Yes. If you see the introduction of the electrostatics, first, what is meant by electrostatics? Electrostatics is nothing but this is a branch of electricity which deals about the study of stationary. Yes. So what I'm saying is electrostatics is nothing but it is a branch of electricity which deals about the study of stationary charges. Stationary charges are nothing but the charges which are at rest. Okay. Now here, if you see the fundamentals about electrostatics, charges are of two types. They are positive charge. The second one is negative charge. Due to the deficiency of electrons or excess of electrons in your body, the charge is formed. Okay. If there is a deficiency of electrons in your body, that body gets positive charge. If there is excess of electrons on your body, then that body will get the negative charge. Right. If the positive charge is given to a body, its mass somewhat decreases because of it lost electrons. If the negative charge is given to the body, since it is taking the electrons, its mass somewhat increases. Okay, so charges are two types. One is positive charge, the second one negative charge. Yes. What are the properties of charge? Properties of charges are one is the charge is a scalar quantity. The charge is a scalar quantity. It is additive in nature. It is additive in nature. That is nothing but the total charge on your body is equal to the sum of charges accumulated at the different parts of the same body. The third one is it is always quantized. Charge is always quantized. That means the charge will be formed on your body is equal to integral multiple of electronic charge or a fundamental charge. Here Q is equal plus or minus NV, where N equal 1, 2, 3 and so on. That means what? Charge can be formed on any body that may be either plus or minus E or plus or minus 2E or plus or minus 3 and so on. Suppose if the body has lost 2 electrons, that gets 2 units positive. If the body has lost 3 electrons, that will get plus 3 units positive charge. If a neutral body gains 1 electron, that will get the 1 unit negative charge, the minus E. If it receives 2 electrons, minus 2E. If it receives 5 electrons, minus 5. In a neutral body, the both positive charge and negative charge are in equal amounts. Therefore, net charge is equals to 0. Whenever two bodies are in the electrification process, then electrons will transfer from one body to another body. So the body who lost the electron will get the positive charge. The body who gains the electrons will get the negative charge. For example, you treat the glass rod with and a silk cloth. This is a glass rod, some others is some silk cloth. When the glass rod is rubbed with the silk cloth, glass rod gets the positive charge and the silk cloth gets negative charge. Okay. Why this is happening? Here the glass rod is losing the electrons, silk cloth gaining the electrons. Okay. Here deficiency of electrons, here existing the excess of electrons. The whatever the number of electrons the glass rod is losing, the same number of electrons will be received by the silk cloth. Therefore, on both glass rod and silk cloth, the charges are in equal amounts and opposite in nature. Okay. Similarly, you can take any example. Ebonite rod is rubbed with wool. Ebonite rod gets negative charge. Wool gets the positive charge. Right. So this is charge quantization. Quantization is nothing but the charge on a body is equal to always integral multiple of electronic charge. The least charge that can be possible on any neutral any body is equal to electron charge, because half electron or fraction of electron is meaningless. The body may lose one electron or two electrons or three electrons. A body will get one electron or two electrons. Therefore, the charge can be formed either plus or minus E or plus or minus 2E plus or minus 3 and so on. Okay. The charge is always conserved. Charge is always conserved means here, for example, if we take this example, before rubbing the glass rod and silk cloth, glass rod has no charge, silk cloth has no charge. Whenever they are subjected to the friction process, glass rod getting positive charge, silk cloth getting negative charge. Here, the total amount of positive charge in the glass rod and the silk cloth, the sum of these two charges again becomes zero. So before rubbing, the total charge is zero. After rubbing, the total charge is zero. Okay. And you take another example. Any nuclear reactions or radioactive decay process, in that reactions also, the charge is always conserved. The charge is always conserved. The total charge is always conserved. It is invariant. That means when the charged body is in the motion, the charge doesn't change. Of course, when it is the rest or it is in the motion, the charge on the body always remains constant. We say that the charge is the invariant. Okay. If the charge is in the accelerated state, that can emit the radiations. That radiation is called Bremsstrahlung radiations. Right. So what I'm saying, the properties of charges are, the one is it is a scalar quantity. It is measured in the units coulomb. Right. It is additive in nature. It is always quantized. It is always conserved. And the charge is a invariant. Right. If you see the Coulomb's inverse pair law, right? The next subcontent, according to our plan, is Coulomb's inverse pair law. What is that? Coulomb's inverse pair law. Coulomb's inverse square law. Yes. Like charges repel each other, unlike charges attract each other. So therefore, there exists either attractive force or repulsion force between any two stationary charges. Let us consider two charges. One is Q1, another is Q2, which are separated by the distance say r in the A. Okay. Then according to Coulomb's inverse pair law, the force of attraction or repulsion, it is directly proportional to product of their charges and inversely proportional to square of the distance. Okay. Then we write F is equal constant K Q1 Q2 by R square, where F is K is the proportionality constant, right? Its value depends on nature of the medium between the charges and also the system of units what we are using. Okay, vectorially we write it as here the Q1 exerts the force on Q2 in this direction. I'm writing it as F211. Q2 exerts on Q1, that is F121. These are equal in magnitude. So whatever the force accepted on Q2 by Q1 equal to the force accepted by Q2 on Q1. That is F12 bar is equal to minus F21 bar. Right? So here, if the medium between the charges is either air or vacuum, then we write the expression F naught is equal 1 by 4 pi epsilon naught Q1 Q2 by R square. Okay, where 1 by 4 pi epsilon naught value equal to 9 into 10 power 9 into 10 power 9 Newton meter square by Coulomb square. From this you can write 1 by 4 pi epsilon naught equal to F R square by Q1 Q2. Force unit Newton, R square meter square, Q1 into Q2 Coulomb square. Epsilon naught stands for permittivity of free space. Epsilon naught is permittivity of free space. Free space. Its value 8.86 into 10 power minus 11 epsilon naught equal. Then Q1 Q2 by FR square. Unit will be Coulomb square by Newton into meters. Okay. If the medium between the two charges is other than vacuum or air, then formula Fm is equal 1 by 4 pi epsilon Q1 Q2 by R square. Okay. Yes. Fm is equal, that is 1 by 4 pi, you can write it as epsilon naught epsilon R Q1 Q2 by R square. Say this is equation 1 and it is equation 2. Right. So here epsilon equal to what substituted? Epsilon equal to what substituted? That is epsilon equal epsilon naught epsilon R. From this epsilon R is equal epsilon by epsilon naught. Yes, I can explain. This is the permittivity of the medium. Epsilon naught permittivity of free space. This is relative permittivity. So relative permittivity can be defined as the ratio of permittivity of the medium to permittivity of free space. From this expression, dividing the equation 1 with the equation 2, then you will get F naught by Fm is equal to this by this. Okay, that equal to epsilon R. From this, Fm is equal F naught by epsilon R. F naught by epsilon R. Using this expression or using this expression, we can define relative permittivity. The ratio of the force between two stationary charges when the medium is air or vacuum to the force between them in the presence of medium is equal to relative permittivity of that medium. Relative permittivity is also called as dielectric constant or specific inductive capacity. Okay, so this is about Coulomb's inverse square law, right? So what I am saying, let me repeat. When the medium between the two charges is F naught equal 1 by 4 pi epsilon naught Q1 Q2 by R square. In the case of other than air or vacuum or in the presence of medium, Fm equal 1 by 4 pi epsilon naught Q1 Q2 by R square. Right? Fm equal F naught by epsilon R. Here epsilon R always greater than 1. Epsilon R for air or vacuum 1. For other dielectric materials greater than 1. Example, if you take the glass, for glass epsilon R equals to 7. For water epsilon R equals to 81. Okay. For good conductors epsilon R equals to infinity. Perfect insulator epsilon R equals to 0. This is the ideal condition, not possible. For any insulator or dielectric medium, then epsilon always greater than 1. Since epsilon R greater than 1, Fm always less than F. Right? So, in the presence of medium, the force between the given 2-point charges is always less than when compared to the force between them in the case of air or vacuum. Right. Now, coming to the next concept, electric field. What is meant by electric field? Electric field. Yes. You consider a positive charge plus Q, then the space around this charge in which it has its influence. That is called electric field. The space around the charge or the region around the charge in which its influence felt is called as electric field. It is two types. Two types. One is uniform electric field. Uniform electric field. Second one, non-uniform electric field. Non-uniform electric field. Okay. Yes. Let us see after defining the electric line of force, how the electric lines of force lie in the uniform and non-uniform electric. Uniform electric field is nothing but electric field strength at every point in the field remains constant both magnitude and direction. In the non-uniform electric field, the electric field strength is not constant. That may change either in magnitude or direction or both magnitude and direction. Right? Okay. So what is meant by electric field strength? Yes. So for example, this is the electric field of the charge plus Q. Now I consider a point P. There I am keeping the unit positive charge. Okay. Then applying the Coulombs inverse square law, let us write the force on unit positive charge. F is equal to 1 by 4 pi epsilon naught Q1 Q2. That is 2 into 1 by, if it is the distance r, this will be r square. This force is equal to the field strength at this point. We write it as E is equal to 1 by 4 pi epsilon naught Q by r square. So how we are defining the electric field strength? The force on the unit positive charge. The force experienced by the unit positive charge placed in the electric field at a point is called as the field strength at that point. So electric field strength is a vector quantity. So write vectorially we write it as E bar is equal to 1 by 4 pi epsilon naught Q by R cube into R, where R cap is the unit vector in this direction. R cap is the unit vector. 1 by 4 pi epsilon naught. It is Q by R square into R cap. R square into R cap. Sorry. Q by R cube into R bar you can. Q by R cube into R bar. Then R bar is the position vector of that point. Right? So field strength is the vector. So what is its direction? So the direction is the force direction acting on the unit positive charge. If it is the positive charge, if this is the unit positive charge, unit positive charge can be repelled in this direction. Therefore, the direction of line of force is in this direction. If you consider the field due to the negative charge, minus Q, then unit positive charge will be attracted by the minus Q. Therefore, the force on unit positive charge is in this direction now. So towards minus Q. Then the electric line's force direction is towards the charge itself. So radially inwards. That's why if you draw the electric lines of force for different charges, that is, I will draw one by one. Due to the positive charge, the lines of force are like this, always moving away from it, radially outwards, radially outwards. Okay, due to the negative charge, due to the negative point charge, then the lines of force are towards itself, radially inwards, like this. Okay, here electric line of force represents what? What is the physical meaning here? On this line, if you keep the unit positive charge at any place, any point, then that can be repelled along this direction because it is a positive charge. It is a positive charge. it can be repelled in this direction. So here, suppose I am keeping the unit positive charge here, then +1 can be attracted by -2 in this direction. The force acting on the unit positive charge is in this direction. Therefore, electric line of force is in this direction. Okay. If you consider both the positive and negative charges, so unlike charges or dissimilar charges, here the line of force always starts from positive charge and that will be ends at minus charge like this. Like this. From positive charge, they are moving away from it. From at the negative charge, they ends here like this. Okay. If you take the like charges, similar charges, plus and plus or minus and minus, since they can be repelled, so the orientation of lines of force will be like this. Right. If you consider the minus and minus, then these are the like charges, so that can be repelled. But of course, here we are showing the direction towards the charge. Right. So these are the orientation of electric lines of force. Now we can say the properties of electric lines of force. Number one, if you observe these lines, due to the single isolated point charge, positive charge, negative charge, or between plus and minus, between plus and plus, whatever it is, here, no two lines of force are intersecting. So that means, suppose if you imagine the lines of force are intersecting at any point. At the point of intersection, you can draw the tangent lines like this. That represents what that means. At that point, electric field strength has the two directions. But electric field strength is a vector point. It is the meaningless. Therefore, no two lines of force intersect each other. It is not possible. Okay, right. When here, in the case of dissimilar charges, the lines are curved lines. On the curved line, at any point, the direction of field strength is along the tangential direction, like this. Along the tangential direction. Okay, here it is very clear. The direction is along that straight line. Between two opposite charges, the direction at any point is along the tangent line direction, keyboard direction. Okay, right. Where the lines of forces are crowded, there the field strength is maximum. The lines of forces are distant, there the field strength will be minimum. Therefore, the lines of force, the electric field strength is directly proportional to number of lines of force existing at that point. Okay. So electric field strength is nothing but what? Electric field strength is the force experienced by the unit positive charge, which is kept in the electric field at any point, is called electric field strength. It is a vector quantity. The unit of field strength is Newton by Coulomb or volt per meter. Okay, Newton by Coulomb or volt per meter. Now coming to the concept, what is uniform and what is non-uniform electric? So here in this region, near the plus Q charge, the lines of force are very closer. As they are moving away from that, the distance between the successive lines is increased. So that means field strength is decreased. Okay, electric field strength is directly proportional to what? The number of lines or electric flux. Electric flux. Okay, in the uniform electric field, the lines of force are always parallel and equidistant lines like this. Best example, you take the parallel plate capacitor. The parallel plate capacitor, of course, it is a positive plate and it is negative plate. Here the lines of force like this. They orient plus to minus. Strictly speaking, but at the edges there may be somewhat curved lines. That is called fringing. But comparing to the area of the plates, if the distance between the plates is very less, therefore this will be neglected. almost between the plates of condenser, the lines of force oriented in such a way that they are equidistant and parallel. Therefore, this is a uniform electric. This is non-uniform electric field. It is non-uniform electric field. It is also non-uniform electric field. Non-uniform electric. In the non-uniform electric field, the lines of force may be chord lines or equidistant lines. Chord lines or equidistant lines. I will draw that figures. In non-uniform electric field, suppose the lines of force are arranged like this. Here, the direction is constant, but the distance between two successive lines is increasing. That represents magnitude is changing. The physical meaning is magnitude changing, but direction is constant. Hence, it is treated as a non-uniform. Okay, if the lines of force are like this, their magnitude as well as direction both are changing. Your distance between two successive adjacent lines remains constant. That represents your magnitude is constant, but the direction is changing because it is a chord line. The direction point to point is changing. Therefore, it is non-uniform electric field. Simply, what I am saying is in the uniform electric field, the electric lines of force are parallel and equidistant. In the non-uniform electric field, they may be straight lines or chord lines. Okay, as shown in the figure. Right? So, in the present class, what we covered is what is electrostatics, electric charge, and their properties. Then after, we discussed about the Coulombs inverse square law and its mathematical expression. Then after, electric field and its types, electric field strength, and electric line of force and properties. Thank you.